Hello, quick question before we start. When you use ChatGPT or Gemini, have you ever wondered what's actually going on inside? Because most of AI you use today traces back to the one paper it called Attention is All You Need. So today, we're going through it. What the problem was, how they solved it, and why it changed everything. So let's get into it. Okay, so before we get into the actual paper, let's start with something everyone's used. Google Translate. You type in a sentence, it spits out a translation. Simple enough, right? But here's the thing, shorter sentences, usually fine. Longer ones, more complex ones, it used to mess up a lot. And there's a real reason for that. That's what this paper is about. Here's a classic example. The animal didn't cross the street because it was too tired. Now, what does it refer to? The animal, right? Not the street. You figured that out instantly, but for a computer, this is generally hard. It could refer to anything earlier in the sentence. The model has to understand the relationship between words that are far apart. That's the core challenge. So, before this paper, the standard approach was something called an RNN, recurrent neural network. The way it works is pretty intuitive actually. It reads a sentence word by word, left to right, like how we read. But the problem is, by the time it gets to the end of a long sentence, it's kind of forgotten what was at the beginning. It has a short memory, and on top of that, because it reads one word at a time, you can't train it fast. You have to wait for word 1 before you can do word 2. No parallelism. Here's what the authors asked. What if we just didn't do that? What if instead of reading word by word, every word could look at every other word at the same time, all at once? That's it. That's the core idea, and they called it attention. Let me make it more concrete. Take our sentence again. When the model is processing the word it with attention, it can directly look at animal across the sentence. It doesn't have to pass through every word in between. The connection is direct. Compare that to a human translator. We naturally focus on the relevant parts of the original sentence when translating each word. Attention lets the model do the same thing. Here's the mental model I find most useful. Think of attention like a spotlight. When the model is working on a specific word, it shines a spotlight on the words it should pay attention to. The brighter the spotlight, the more attention it gets. And the key thing, all the spotlights turn on at the same time, not one after another. Right, so the architecture they built around this idea is called the transformer. It has two main parts, an encoder and a decoder. The encoder reads and processes the input. The decoder generates the output. In translation, the encoder would read the English sentence and the decoder would write out the French. Each side has 6 layers stacked on top of each other. We will look at what's inside those layers in a sec. Let's get into the actual mechanism. Attention is built on three things: query, key, and value. These sound technical, but the intuition is really simple. I'm going to use a library analogy. Query is what you're searching for. Think of it like typing something into a search bar. The word it in our sentence is basically asking which other words are relevant to me right now. Every word in the sentence generates its own query, its own search request. That's cute. Key is what each word broadcasts about itself, like the title of a book in a library catalog. Animal might have a key that says, I am a living creature. I am the subject of this sentence. When you match the query against all the keys, you get a score. How relevant is this word to what I am looking for? In our example, it querying animal gives a very high score. That's K. And value is the actual content that gets passed along. Once we know how much attention to give each word, based on those scores, we collect information from them using values. The final output for each word is basically a weighted mix of all the values, where the weights are the attention scores. So if animal got a high attention score, its value contributes a lot to how we understand it. That's the whole thing, QKV. And here's the actual formula. Don't panic. It's simpler than it looks. You take Q.K, that's the similarity score, divide by the square root of D to keep numbers stable. Apply softmax to turn it into percentages. Multiply by V, that's it. 4 steps. The whole attention mechanism in one line. So one attention head is good, but the authors realized, what if we ran several of them at the same time, each looking at a different type of relationship? One head might focus on grammar, another on meaning, another on position. They used 8 heads. That's multi-head attention. All 8 run in parallel, and the outputs get combined. The result is a much richer understanding than any single head could produce. Visually it looks like this: 8 separate attention operations, all running at the same time. Each one specializes in something slightly different. Then they all get concatenated, joined together, and passed through one more linear layer. The final output is way more expensive than a single attention had ever could be. Here's something subtle. Attention by itself has no idea about word order. Dog bites man, and man bites dog. Totally different meanings, same word. To solve this, they added positional encoding. Each position in the sentence gets a unique signal based on sine and cosine functions, kind of like a mathematical fingerprint for each position. The signal gets added to the word's representation before it goes into the model. No extra training needed. Let's open up one encoder layer and see what's actually in there. First, you've got multi-head self-attention, all words looking at each other. Then a feed-forward network that processes each position independently. And between each of those, there's an add normalize step. That's a residual connection plus layer normalization. It basically preserves the original signal so it doesn't get lost as you go through 6 layers. This entire thing repeats 6 times. The decoder is similar, but with one extra piece. It has a masked self-attention. When generating word 4, it can see words 1 through 3, but not beyond. No picking ahead. And then there's cross-attention, which is really the key thing. This is where the decoder actually reads what the encoder understood about the input. Without cross-attention, the decoder would have no idea what the original sentence was. Trace through a full translation. You feed in the cat sat on the mat. Positional encodings get added. It goes through 6 encoder layers, producing a rich internal representation of the sentence. Then the decoder starts. It gets a start token. It uses cross-attention to look at the encoder's output, predicts the first word, Li, then the second, chat, and so on, one word at a time, until it predicts an end token and stops. Quick one here. Residual connections, also called skip connections. After every sub-layer, the input to that layer gets added back to its output. The formula is just output equals layer norm of x plus sub-layer of x. What that means practically is, even after 6 layers deep, the model still has direct access to the original word representations. Information doesn't get crushed as it goes deeper. The model was trained on massive datasets: 36 million English-German sentence pairs, 45 million English-French, just 8 GPUs, and the base model trained in about 12 hours. For comparison, previous state-of-the-art models took days to weeks. The efficiency wasn't just a nice bonus, it was kind of a big deal on its own. And the numbers, on English to German translation, the transformer hit 28.4 BLEU score. The previous best was 26. That's a big jump. On English to French, it matched and slightly beat the best previous model. Oh, and the training cost? A fraction. The big transformer model cost around $300 to train. Previous state of the art was over 1,000. Better research, cheaper to run. What's really interesting is they didn't just test on translation. They also threw the same architecture and English consistency parsing, basically understanding the grammatical structure of a sentence, and it achieved the state of the art on that too. With barely any changes to the model, that's when it became clear. This isn't a translation trick. This is a general purpose way to learn relationships in sequences. And this is where it gets kind of wild. BERT, which powers Google search, transformer encoder. GPT-1234, transformer decoder. ChatGPT, fine-tuned GPT. Claude, transformer-based. Gemini, transformer-based. Every major AI model you interact with today traces directly back to this one paper. That's not exaggeration. So why did it win so completely? Four things. First, it's parallelizable. GPUs love running things in parallel, and transformers let you do exactly that. Second, any two words connected directly, no matter how far apart they are in the sentence. Third, it scales. Just make the model bigger and it gets smarter. And fourth, it works on basically anything that's a sequence. Text, code, audio, images, protein structures, the same architecture. To be fair though, it's not without issues. The biggest one is quadratic complexity. Attention between n words requires n squared operations. So, for a very long document, it gets really expensive really fast. There's also the memory issue. All those Q, K, V metrics for long sequences eat up a lot of GPU memory, and early transformers had a fixed maximum context length. Models since then have worked hard to fix these, but they are real limitations of the original design. Just to put the impact in perspective, this paper has around 170,000 citations. The average top machine learning paper gets maybe 500. It's generally one of the most cited papers in the history of computer science, not just AI computer science. Right, five things to walk away with. 1. Attention lets every word look at every other word directly. 2. Q asks what to look for. K describes what each word contains. V is what gets passed on. 3. Multi-head attention runs 8 of these at once, each picking up different patterns. 4. The transformer is faster, more scalable, and more general than what came before. 5. Every AI assistant you use today is running on this. Personally, what I find most remarkable about this paper is the benchmark numbers. It's the title, Attention is all you need. They weren't hedging. They weren't saying attention might help or attention is one useful component. They said this is all you need. And they were right. The whole field had been adding complexity on top of complexity, and these 8 people stripped it all away and showed that one clean mechanism was enough. The kind of confidence is rare, and it turned out to be completely justified. So that's the paper. RNS read word by word. Slow, short memory couldn't scale. Attention fixed that. Every word looks at every word all at once. They wrapped into the transformer, decoder, encoder, 6 layers each. Beat every benchmarks. And then ChatGPT, Gemini, Claude, all of it came from here. That's attention is all you need.